Okay, hi everyone, I'm Victoria,
I'm Laura.
I'm Julia.
and today our project is on the Goldbach conjecture. So first, let's start off by talking a little bit about Christian Goldbach. So he was a Russian mathematician born in 1690 and died in 1764. He mainly studied law and medicine and only really got into mathematics in his later years, around his early 20s. He is known for his groundbreaking discoveries in number theory and studied at the University of Königsberg in Russia. Goldbach traveled all of Europe, meeting leading scientists who shaped his findings. Some of these scientists include Bernoulli, Belfinger, and most importantly, Euler. So to understand Goldbach's influence in mathematics, we must first understand the politics in Russia during the 1700s. So Peter the Great and his wife Catherine ruled Russia from 1682 to 1725. They were a driving force in setting up the Imperial Academy of Sciences, which was the highest scientific institution in Russia. Followed by the death of Peter the Great, Goldbach tutored his 11-year-old son, Peter II. So this is where Euler and Goldbach met and started their 35-year-long correspondence. So although there were frequent changes in politics in Russia, Goldbach managed to remain in politics and teaching children of royalty. He was very well liked. So there were many influences in Goldbach's life. However, the most important was Euler. So they met at the academy in 1727. They wrote almost 200 letters back and forth to each other. And in 1742, within a letter, Goldbach first proposed the Goldbach conjecture. Throughout many of their letters, Euler and Goldbach proved that the conjecture was true for even numbers up to and including 2,500. However, there is no mathematical proof or formula that proves this to be true. Within these letters between Euler and Goldbach, they discussed topics involving number theory, infinite series, complex numbers, and prime numbers. In specific, they discussed Fermat's numbers, Mersain's numbers, perfect numbers, polynomials representing prime numbers, and Fermat's last theorem. So here is an example of original letters that they had written back and forth to each other. However, they are in Russian, but as you can see, they were fairly short letters that they would write back and forth to each other about mathematics and questions and trying to figure things out. Goldbach made successful advances in the theory of curves and the integration of differential equations. He proved a few conjectures on perfect powers. However, the Goldbach conjecture is still today not proven. In 1742, as mentioned, Christian Goldbach wrote a letter to Leonhard Euler in which he proposed his binary conjecture, which states that every integer n greater than 2 is the sum of two primes. If solved, the Goldbach conjecture would extend mathematicians' understanding of the distribution of prime numbers. In his letters to Euler, Goldbach proposed a ternary conjecture. It claims that every odd number n greater than 5 is the sum of three prime numbers. If the strong conjecture is solved, the ternary conjecture, otherwise known as the weak conjecture, would constitute a corollary. Over many centuries, there have been numerous attempts in proving Christian Goldbach's conjecture. In 1938, Niels Pipping verified that the Goldbach conjecture was true for even numbers up to and including 100,000. In 2012, mathematicians confirmed that it was true for even numbers up to and including 4 times 10 to the power of 18. However, only a general proof can validate his conjecture. The greatest advancement towards this milestone and in the field of number theory was notably in 2013, when Harald Helfgott proved Goldbach's ternary conjecture, also known as the weak conjecture. Helfgott's approach to the proof entails a detailed and comprehensive technique known as the Hardy-Littlewood-Vinogradov circle method. His work stems from analysis in the complex plane and aims to represent number sets in terms of integrals over circles, conveying greater insight into minor arc estimates. While it is true that proving the strong conjecture would imply the weak conjecture, the converse is not true. So you might be asking, why is his weak conjecture a consequence of the strong? Well, if given an odd number d greater than 5, we know that d take away 3 is even and greater than 2. Thus, if the strong conjecture held true, we would get d take away 3 equals p plus q, where p and q are two prime numbers. Then d equals 3 plus p plus q would result in the sum of 3 primes.
To understand the Goldbach-Bertrand theorem, first we must understand dash line theory. So dash line theory, it's a mathematical theory which studies the connection between the sequence of natural numbers and their divisibility relationship. To start the development of the dash line theory, we must observe the sequence of prime numbers. So here we have the numbers 2, 3, 5, 7, and so on. If we add 2 to all other prime numbers, we get 4, 5, 7, 8, 13. And if we were to add 3, we would get 5, 6, 8, 10, 12, 14, so on. Continuing this results in the following table, in which every column contains the value of the sum, every row contains the first addend, and their intersection contains the second. In reference to table 1, the Goldbach conjecture states that the columns corresponding to even numbers greater than or equal to 4 are never empty. Here we want to replace the cell numbers with the dash. This results in the following table. To see how the table representing a dash line of the kind 2, 3 to n is related to prime numbers, let us divide table 2 into 3 sections. Here we have an initial part, which is comprised of columns 0 and 1. Each column is special because by construction, column 0 contains a dash in each row, whereas column 1 doesn't contain any dashes. Next, we have a central part comprising of columns 2 to 5, and a final part made up of columns 6 and on. In analyzing table 3 from the perspective of prime numbers, we note that in the central or the yellow section, all of the columns containing one dash are prime numbers. So we see 2, 3, 5 only have one dash. In the final or the green section, all of the columns not containing a dash are prime. Here we have 11, 13, 17, 19, etc. Both properties derive from the fact that prime numbers are divisible by 1 and itself. In the column of a prime number p, up to one dash can be present in the row of the component p, if p is a component of the dashed line. If column p contains just one dash, it means that p is divisible by just one dash line component. That is, by just one number in the set 2, 3 to n. However, that does not imply p to be prime. If p belongs to the central part, then p is a component. Since p is obviously divisible by itself, there is a dash at the intersection between the row associated with the component p and the column p. Since the dash of the column p is situated in the row associated with the component p, p is not divisible by the other dash line components. Therefore, p is prime. In the final part, the converse is verified in table 4. If a number is not divisible by 2, 3, 4, or 5, it does not mean that it is prime, because it may be the product of a prime greater than 5. For example, 49 has no dashes. However, 49 is not a prime number, as it is the product of two primes greater than 7, otherwise known as 7 times 7. In the representation of a dashed line, columns without dashes are called spaces. Generalizing the previous argument and introducing the concept of space gives the following property. So it's the property of spaces and prime numbers. In the representation of the linear dash line 2 to n, all the columns between 2 and n are prime numbers if and only if they contain one dash. All of the columns between n plus 1 and p squared minus 1 are prime numbers if and only if they are spaces, where p is the smallest prime number greater than n. All of the columns from p squared that are primes are also spaces, but there exist spaces that are not primes. Now, to understand the Goldbach-Bertrand theorem, let us prove two additional properties. So first we have the property of symmetry of factorization dash lines. So in the factorization dash line of a number m, the columns from 0 to m are symmetrical. So the column I coincides with the column m minus I for each I equal to 0 all the way to m. Next, we have another property about the prime spaces on the right side of the factorization dash line of an even number. In the factorization dash line of an even number 2n, all prime numbers p such that n is less than p, which is less than 2n, are also spaces.
All right, so here we have the Goldbach-Bertrand theorem with its formulation similar to Goldbach's conjecture and its proof using the Bertrand postulate. So the theorem states that every even number, 2n greater than 2, can be written as the sum of two integers, one of which is prime and the other is coprime with 2n. In order to prove the theorem, firstly, we have to build the factorization dashed line T of 2n. And due to Bertrand's postulate, there is certainly a prime P that falls between n plus 1 and 2n. We know that since P is a prime number, due to the property of prime spaces on the right side of the factorization dashed line of an even number, that it is also a space of T. And since the dashed line T is symmetrical, also due to the property of symmetry of factorization dashed lines, we know that also Q is defined to be equal to 2n minus P and is in turn another space. Since Q is a space, by definition, it is not divisible by any of the components of the dashed line. And hence Q is not divisible by any of the prime factors of 2n. And by definition, we also know that Q is coprime with 2n. Furthermore, we ultimately have that P plus Q is equal to 2n. And overall, we have found two numbers, P and Q, of which P is prime, Q is coprime with 2n, and their sum is 2n, which was what we initially sought to prove. And just a little remark. So contrary to the Goldbach conjecture, the Goldbach-Bertrand theorem does not consider the expression of an even number 2n as the sum of two identical prime numbers. So for instance, we have 2n is equal to p plus p, with p being prime. So according to the Goldbach-Bertrand theorem, one addend must be prime while the other must be coprime. So if both addends were equal to the same prime p, then that P must be coprime with 2n, and that's not possible here. So in fact, if 2n equals P plus P, then 2n is equal to P. Therefore, we know that the lowest common multiple of 2n and P is equal to the lowest common multiple of 2P and P, where P is greater than 1, whereas the lowest common multiple of 2n and P is equal 1, if 2n and p are coprime. And in the Goldbach-Bertrand theorem, the coprime number can be 1, but that is not true for the Goldbach conjecture. So we must also note that the coprime number must be odd. If it is coprime with 2n, it cannot have 2 as a prime factor. Similar to the ternary conjecture, the Goldbach binary conjecture implies the Bertrand postulate. And now let us consider an example of the decompositions of the number 14 that follow in compliance with the Goldbach-Bertrand theorem. So the decompositions of 14 must respect the given condition of which the first addend must be prime. So as follows are all the possibilities of addends which actually do follow this condition. So we see 14 is equal to 2 plus 12, 3 plus 11, 5 plus 9, 7 plus 7, 11 plus 3, as well as 13 plus 1. And after considering this, next we must review the decompositions in order to see which equations actually satisfy the condition that is which equations have a second addend that is co-prime with 14. So of the second addends, it actually is only 11, 9, 3, and 1, which are co-prime with 14. We recognize 12 and 7 are not co-prime, as the lowest common multiple of these are not the same. Thus, in order to satisfy the Goldbach-Bertrand theorem, we consider the following decompositions. So we have 3 plus 11, 5 plus 9, 11 plus 3, and 13 plus 1. The decomposition 7 plus 7 is not listed, although it does accord with Goldbach's conjecture. And the decompositions 5 plus 9 and 13 plus 1 are not compliant with the Goldbach conjecture, since 1 and 9 are not prime numbers. And in addition, we can also completely remove the decompositions of 3 plus 1 and 11 plus 3, since these addends are actually commutative. They follow the commutative property. Yeah, and that's it for our presentation. So thank you for listening.